Hey everyone, welcome back to the channel. Here we talk all about tech careers, interview strategies, and how you can land your dream job in cybersecurity, data engineering, and cloud computing. Today's video is a really exciting one. We're diving into senior lead cloud data engineer interview questions and answers, specifically geared toward candidates applying for cloud-heavy big data roles like at Cox Enterprises and similar top companies.
Before we jump into the interview prep, let's take a quick moment to talk about what data engineering actually is. Data engineers are the builders of the tech world. They design, construct, and maintain scalable data pipelines, ensuring that organizations can store, move, transform, and analyze huge volumes of data efficiently. Without great data engineers, businesses would struggle to get the right information to make smart decisions.
And today, data engineering is one of the most in-demand roles across industries, from finance and healthcare to tech giants like Amazon, Google, and Microsoft. If you're looking to break into this field or take your career to the next level, mastering cloud platforms like Azure, data pipeline architecture, big data tools like Spark and Databricks, and ETL best practices is essential.
In this video, we're going to walk you through some real technical interview questions for a senior lead cloud data engineer role. And not just the questions, but also strong sample answers so you can see exactly what hiring managers are looking for. This will help you understand the kind of depth they expect at the lead level, structure your responses clearly and professionally. Stand out as a top candidate by demonstrating both technical and leadership skills. If you're ready to boost your interview game and move one step closer to landing your next big data role, then let's dive into the questions.
How would you design a scalable and secure data pipeline architecture using Azure Data Factory and ADLS?
First, I would start by thoroughly understanding the data sources, volumes, and usage patterns to ensure the architecture can accommodate current and future requirements. This would involve mapping out the various data sources, on-premises, cloud-based SaaS, APIs, etc., the frequency and volume of data, and the downstream consumption needs. With this information, I can then plan an architecture that can scale seamlessly as the data landscape evolves. For the core data pipeline, I would leverage Azure Data Factory as the orchestration service to manage the end-to-end data ingestion, transformation, and loading processes. ADF provides a range of built-in connectors and activities that can be used to ingest data from diverse sources, apply complex transformations using languages like Python and PySpark, and load the processed data into ADLS. To ensure scalability, I would architect the pipeline to leverage Azure Databricks for compute-intensive transformations, taking advantage of the powerful distributed processing capabilities of Apache Spark. Additionally, I would implement partitioning and partitioning strategies within ADLS to optimize data access and query performance. Regarding security, I would implement a robust identity and access management (IAM) strategy using Azure Active Directory (AAD) to control access to the data pipeline and ADLS. This would involve setting up appropriate role-based access controls (RBACs) and managed identities for the different components of the architecture, ADF, Databricks, ADLS. Furthermore, I would leverage Azure Key Vault to securely store and manage sensitive credentials, API keys, and connection strings used throughout the pipeline. Data encryption at rest and in transit would also be a key consideration, with the use of technologies like Azure Storage Service Encryption. To ensure the reliability and recoverability of the data pipeline, I would implement comprehensive monitoring, alerting, and error handling mechanisms using features like ADF's built-in monitoring and Azure Monitor. This would allow for proactive detection and resolution of issues, as well as the ability to quickly roll back to a known good state in the event of data corruption or pipeline failures.
Question, what are best practices for implementing a lakehouse architecture on Microsoft Fabric or Databricks?
Implementing a lakehouse architecture on Microsoft Fabric or Databricks requires following a set of best practices to ensure the solution is scalable, efficient, and aligned with modern data engineering principles. First and foremost, I would start by defining a robust data governance and data modeling strategy. This would involve establishing a clear data catalog, defining data schemas and partitioning schemes, and implementing appropriate data security and access controls. On Fabric, this could be achieved through the integration of Azure Purview for data cataloging and governance, while on Databricks, Delta Lake would be a key component for enforcing schema management and ACID transactions. Next, I would focus on optimizing the data ingestion and processing pipelines. On Fabric, I would leverage Azure Data Factory and Azure Databricks to orchestrate the end-to-end ETL/ELT workflows, taking advantage of native integrations and the ability to scale compute resources on demand. On Databricks, I would utilize the Databricks Lakehouse platform to seamlessly ingest data from various sources, apply transformations using PySpark or SQL, and persist the processed data in a Delta Lake. Additionally, I would implement partitioning, bucketing, and other performance optimization techniques to ensure efficient data querying and analytics. To ensure the Lakehouse architecture is scalable and fault-tolerant, I would design the data storage layer using Azure Data Lake Storage, ADLS, Gen 2, or Databricks Delta Lake. These technologies provide the necessary features for handling large data volumes, supporting incremental data updates, and enabling fast, reliable data access.
Question, how do you approach setting up role-based access control, RBAC, and Azure AD integration for securing Azure resources?
Setting up role-based access control, RBAC, and Azure Active Directory, Azure AD integration is a critical aspect of securing Azure resources. As a senior lead cloud data engineer, I would approach this in a structured and comprehensive manner, following industry best practices. First, I would start by thoroughly understanding the various Azure resources, their corresponding data and functionality, and the different personas and roles that need to interact with them. This could include data engineers, data scientists, business analysts, IT administrators, and other stakeholders. By mapping out the users, their responsibilities, and the required access levels, I can then design an RBAC model that aligns with the organization's security and compliance requirements. Next, I would leverage Azure Active Directory, Azure AD, as the identity management service to authenticate and authorize users and applications accessing the Azure resources. To implement the RBAC model, I would utilize the built-in Azure role definitions, such as Storage Blob Data Contributor, Databricks User, and Data Factory Contributor as a starting point. Additionally, I would create custom role definitions to address any specific access requirements that are not covered by the out-of-the-box roles. To ensure the RBAC and Azure AD integration remain effective and up-to-date, I would implement a robust governance and monitoring framework.
Question, can you explain how you would architect an end-to-end ETL solution in Azure integrating DevOps for CI/CD?
First, I would start by defining the data sources, target data models, and the overall data processing requirements. This would involve mapping out the various on-premises, cloud-based, and API-driven data sources, understanding the data volumes and update frequencies, and aligning the ETL workflows with the organization's analytical and operational needs. Next, I would leverage Azure Data Factory, ADF, as the core orchestration service to manage the end-to-end ETL pipelines. ADF provides a range of native connectors and activities that can be used to ingest data from diverse sources, apply complex transformations using languages like Python and PySpark, and load the processed data into target data stores. To ensure scalability and performance, I would integrate Azure Databricks or Azure Synapse Analytics as the compute layer for data processing and transformation. To integrate DevOps principles, I would set up a CI/CD pipeline using tools like Azure DevOps or GitHub Actions. This would involve the following steps: version controlling the entire ETL solution, including ADF pipelines, Databricks notebooks, and any custom code in a Git-based repository. Implementing automated build and deployment processes to package the ETL components and deploy them to the appropriate Azure environments, e.g., development, staging, production. Incorporating automated testing, linting, and code quality checks to ensure the reliability and maintainability of the ETL solution. Leveraging Azure Key Vault to securely store and manage sensitive credentials, API keys, and connection strings used throughout the ETL pipelines. Implementing infrastructure as code, IAC practices to provision and manage the underlying Azure resources, e.g., Data Factory, Databricks, ADLS, as part of the CI/CD pipeline.
Question. Can you explain the differences between star schema and snowflake schema in data warehouse design?
When it comes to data warehouse design, the choice between a star schema and a snowflake schema boils down to a trade-off between simplicity and flexibility. The star schema is the more straightforward approach, with a central fact table surrounded by denormalized dimension tables. This results in faster query performance, as there are fewer join operations required. It's well suited for classic business intelligence and reporting use cases. In contrast, the Snowflake schema normalizes the dimension tables, breaking them down into multiple related tables. This can improve data integrity and reduce redundancy, but increases the complexity of queries, potentially impacting performance. The Snowflake schema is more appropriate when the data relationships are complex and data integrity is a primary concern. The added flexibility of the normalized dimensions may outweigh the performance trade-offs for certain analytical use cases.
Question. How do you ensure data reliability engineering DRE standards in your data pipelines?
To ensure data reliability engineering, DRE standards in my data pipelines, I would leverage cloud-native tools to track pipeline performance, data quality, and potential issues. Establish clear alerts and incident response procedures. Incorporate fault tolerance and resilience. Adopt a DevOps approach. Optimize for cost and scalability. Continuously monitor and optimize resource utilization and costs. Integrate with data catalog and governance solutions for data traceability. Establish clear data ownership and stewardship responsibilities. By focusing on these key areas, I can ensure my data pipelines adhere to industry-leading DRE standards, delivering reliable, scalable, and well-governed data solutions.
Question. How have you integrated APIs, REST, SOAP into your ETL pipelines for real-time data ingestion?
Integrating APIs into ETL pipelines for real-time data ingestion is a core part of my approach as a senior lead cloud data engineer. Here's how I typically handle it. API catalog. I maintain a detailed catalog of the available APIs, their endpoints, authentication requirements, and data schemas. This allows me to quickly identify integration points and address any changes. Secure connectivity. I leverage API management services like Azure API Management to centralize the authentication and authorization logic. This ensures secure, scalable access to the various API data sources. Real-time ingestion. I design dedicated pipeline components that can continuously poll or subscribe to API data feeds, enabling the near real-time ingestion of information into the data platform. Handle API constraints. Understanding API rate limits, throttling, and other constraints is crucial. I implement robust retry mechanisms, back-off strategies, and other techniques to gracefully handle these limitations. Data quality. Rigorous data validation is a must. I set up comprehensive checks and alerts to monitor the quality of the API-based data, ensuring it meets the organization's standards. Scalability. To support the high-velocity nature of API-driven data, I leverage cloud-native services and architectures that can scale seamlessly as demands fluctuate. Observability. Integrating the API-based ingestion workflows into the overall pipeline monitoring and observability strategy is key. This allows me to quickly identify and address any issues that may arise.
Question. Can you explain some cloud-native architectural patterns you've used when designing big data solutions on Azure or AWS?
When designing big data solutions on Azure or AWS, I leverage several cloud-native architectural patterns. Serverless ingestion. I use Azure Functions or AWS Lambda for event-driven, scalable data ingestion, integrating with services like Event Hubs or Kinesis. Parallel processing. I set up scalable distributed environments with Azure Databricks or AWS EMR, optimizing for Apache Spark's inherent parallelism. Data Lake Foundation. I implement a data lake using ADLS Gen 2 or S3, integrating with metadata management to enable discovery and governance. Microservices and events, I decompose the solution into loosely coupled, scalable microservices, adopting an event-driven architecture with technologies like Service Bus or Kafka. Infrastructure as code, I automate provisioning and configuration using Terraform, ARM templates, or CloudFormation for consistent, repeatable deployments. Observability, I leverage Azure Monitor, CloudWatch, and Grafana to gain full visibility with centralized logging, metrics, and alerting. Cost optimization, I continuously monitor and optimize resource utilization and costs, leveraging strategies like spot instances and serverless approaches.
Question, how do you prepare technical user stories for an agile data engineering project?
When preparing technical user stories for agile data engineering projects, I take a structured yet personalized approach. I thoroughly engage with stakeholders to deeply comprehend the underlying business requirements and objectives. This allows me to translate high-level needs into tangible technical user stories. For each user story, I clearly define the acceptance criteria, outlining the specific functionality, data requirements, and performance expectations. This ensures the stories are well scoped and provide a clear path to validation. I leverage my deep technical expertise to identify the necessary data engineering capabilities, tools, and architectural patterns. This allows me to incorporate the right technical details into the user stories. I work closely with the product owner to prioritize the user stories based on business value and technical dependencies. I also sequence the stories to ensure a logical, incremental delivery of the data engineering solution. I actively collaborate with the cross-functional Agile team to refine the user stories, clarify any ambiguities, and align on the implementation approach. This promotes shared understanding and ownership of the technical deliverables. I ensure the user stories are clearly linked to the overarching data engineering roadmap and architectural design.
Question, describe a time when you had to influence the data strategy or architectural decisions in a large organization. What approach did you take?
In my experience as a senior lead cloud data engineer, there was one particularly impactful situation where I had to influence the data strategy and architectural decisions within a large, complex organization. The organization was going through a digital transformation, and they had several disparate data sources and legacy systems that were hampering their ability to derive insights and make data-driven decisions. The existing data infrastructure was fragmented, with siloed data warehouses and a lack of centralized governance. When brought in to assess the situation, I recognized the need for a comprehensive, cloud-based data platform that could unify the organization's data landscape and enable advanced analytics capabilities. However, getting buy-in for this significant architectural shift was going to be a challenge, as there were entrenched stakeholders and teams resistant to change. I took a comprehensive collaborative approach. I engaged stakeholders to understand pain points and priorities, tailoring my recommendations. I rapidly built a POC to demonstrate the power of a cloud-native data platform, generating excitement. I quantified the business value, securing executive sponsorship for the strategic importance here. I advocated for an incremental rollout to build trust and expand scope gradually. I collaborated with change management to ensure a smooth transition and user adoption. This balanced technical expertise with stakeholder management and change leadership, enabling me to successfully transform the organization's data and analytics capabilities.
All right, everyone, that wraps up today's interview prep for the senior lead cloud data engineer role. I hope these questions and answers gave you a clear idea of what to expect and how to absolutely crush your next interview.
If you found this video helpful, please take a second to give it a thumbs up. It really helps more people find this kind of content. And if you want even more tech career tips, detailed interview guides, and success strategies, don't forget to hit that subscribe button and turn on the notification bell so you never miss an update.
Thanks so much for watching. I'm rooting for you, and I'll see you in the next video.